universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hey, welcome everybody to SkyTour live stream. How are you? It's good to see you guys. I am here tonight to do a nice stream with you guys. I just came off the radio show, which a lot of you were there. Nice Duffy, Cosplay, and Rockstar's with us. Dale, how you doing? And Marco's with us. Hey, Marco. These are the early attendees. There'll be more. So it's good to see you guys. Daisy and Sophie are with us. Hey there. Nice to see you guys. All right, let's move a little bit over here. Cosmic Ray has a request, lowers Nebula, which we've done before. But we may do it again. We'll see. It's sharpness 280. Okay. Step further, I'm just gonna just do this. Let me get my alignment here. synchronization is very important. Get the coordinates lined up. And what we're going to do next is move to an object. And Ray, remind me after we do this. I'm going to do an object first. You'll notice we've got some wind blowing out there, so I'm not sure how successful this will be, but we'll give it a shot. We're going to go to the Witch's Head Nebula. And I'm going to go to this section of the nebula. Right here, the top part, right there. Let's first bring up our field of view. The red square rectangle outlines the field of view of this particular telescope right now. So let's do this section of the Witch's Head. And we're going to say go to that spot in the sky. So now we move over just to that spot. So we'll center on here. So at this particular location, Witch's Head, you can even sort of see it here, starting to show up. We're going to wait for the edge of it's right there. Actually, this might be perfect. We're going to wait for this to calm down and get a guide star going. We already got guiding going on. We have the, see that? Like, see what that's doing? That's bad. That's the, there's the desert winds. And the desert winds are actually, I know why the problem with the music is because I'm not high enough. I just realized my my volume was down a little bit, but I'll drop the music a little bit. Thank you, Michael Hedrick, for the reminder. So, here we go. All right, so now we'll go in and take a look now. Let me make an adjustment here. I think this will give me a little better outlook here. 1, 2. Hey, look at getting there. 1, 2, 3, 4. All right, just getting my gain up there. All right, Doc Holliday, how you doing? Nice to see you. Yeah, I got the music turned down now, and I noticed that my volume was just a little low for some reason, but I will keep the volume low so that you can hear me over the music. So that said, let me look at something while I got this here. First things first, I'm going to start an exposure here, and we're going to hope this is going to work because of the fact that it's actually quite quite emblematic of the problem. I'm going to do a 25-second shot here, and we're going to take off our low light view and go into a live stack mode. And we'll wait for this image to come in. Meanwhile, I'm going to check out a parameter that I need to look at right here. Okay, let's do this here. I think this is the one I want right here. 1, 2. Hey, there we go. That puts me up there a little more. That's good. And I think that we should be good now. You guys can let me know in the chat. Okay. Hey there, Calabos. How you doing? Nice job today, Calabos, in giving away a pair of binoculars on our radio show. Ronald ERRT Radio won them. He was closest with his guess. Let's see what our filter's showing. Yeah, we're actually a little too high, but this will still produce round star images if I go right about here. So now I think this will work fine. Yeah, I'm trying to do that. Hold on, volume wise. Okay, there we go. There's one. Is this any better? I hope this is better, because I'm going to try very hard to do this. Of course, I also just came off a radio show, so my voice is already strained as it is. All right, let's try this guy now. Yeah, there it is. You can still see that very clearly. Okay, so now, thank you so much, guys. Let's color correct this, which will help bring out some of the Nebula colors. All right. And we're going to zoom this so that we can move our level with very, very precise accuracy. And we have 3 frames that we've captured and 2 that we've rejected, as you can see right there. So it shows that we've actually got we have a loser acquisition, an average loser acquisition right here. There we go. This is better. Now let's color correct. We still have the remnants of the sunset happening, so that's what these little this reddish hue is in here. We're getting a little bit of the sunset there. Hi, Cindy Murphy. I want to thank those of you that came out in the radio show earlier. That was very nice. Hello, Annie Lane. How are you? I think my voice should be better now, Annie. I see what happened. Actually, I didn't have Skype running. If I have Skype running, it's weird because then suddenly it sounds better. And I don't know what Skype's doing to actually amplify my voice, but it does. So that's crazy. Right? James Hyatt says, first time seeing the radio show. Oh, that's cool. I'm glad that you actually watched it today, James. It's a weekly show about astronomy. Tonight's show was just a little weirdly different. Bill came on. He's our producer, and he always has so much to say. So it was kind of funny. But then we have Tara Diulis, who is one of the SkyTour Livestream nonprofit company officers. Marianne Robb is also one. She may be in the chat in a little while. So that'd be kind of cool. So, that said, I am going to continue to expose. Here we did 7. We've captured 8 with 2 rejections so far, so we haven't upped that at all. Seems like we're doing okay. So I'm going to try and reduce a little bit of the background noise. There we go. A little bit of that red color, get rid of it. Yeah, so that kind of pulls out the... Okay, that's a little bit better. Let me see if I can get a proper color match. Because right now with the sun setting, we end up with a really thank you, Annie. With the color, I'm sorry, with the sun setting, the color of the sunset will stop infecting our imagery very shortly. And I just wanted to get started early with you guys. Because I just came from a radio show, so I figured, hey, while I'm sitting here, let's do this. For those that don't know me, my name's Mark D'Antonio. I am an astronomer. That's what I went to school for. This is what we look like. And I took my astronomy to the public outreach sector. I felt that, I had the opportunity to go all over the world to study in different observatories. I got accepted at some good schools, and I was going to go to Chile, but I decided not to because my heart wasn't in it, because I felt like I really wanted to get people excited about this. And this is how you do it, showing them this is live. This is not Memorex. No, this is live. It's not something that is a photo that we're just pulling up and saying, look at this picture taken by the Hubble. This is a picture taken by a telescope. That telescope right there, you're looking at it. And I'm in Connecticut, and that telescope is 2,500 miles away out in the Arizona desert. And I'm running it from Connecticut. Everything you see on the screen, I'm running from Connecticut. So, and the reason I'm doing that is because I figured out how to remotely operate these things out there, and I think that's pretty cool. This is the first of 2 observatories we're putting out in the desert. The second one will be coming along as soon as we can scout another site. We have another site that we're going to be looking at the end of this month, or near the middle of this month, middle to end. And so we'll be able to know for sure whether we're going to put this next system at this new site. And we may have a few surprises in store. Now, the other thing, too, I wanted to mention to you guys, we have been primarily looking at night sky stuff. But you know what? We have a whole daytime that goes by that we don't see anything, right? Well, we're going to try and change that. Here's what we're going to plan on doing. Okay. I may have the opportunity to get a solar telescope. And if I do, I'll make that the SkyTour Livestream East telescope. And so during the day, we'll be able to look at the sky and look at the sun and see all the prominences and the flares and study the sun during the day. And at night, we can study the stars. So that way, I'm fully rounded. Won't that be cool? So it's a thought. Now, Michael Hedrick says, okay, he's talking about eccentricity. Mark, do other moons have greater eccentricity than ours? Do galaxies also have this in relation to space? Well, that's a good question. Galaxies move so slow relative to each other that it's hard to gauge an orbit of a galaxy around another galaxy. As far as other planets and moons, yeah, and so forth, and minor planets, oh sure. There's a lot of highly elliptical orbits out there, many in the comet realm. Many comets have highly elliptical orbits. Pluto's orbit's a little bit elliptical. Our orbit is a little bit elliptical. The moon's is slightly elliptical. It's not a perfect circular orbit, in other words. And you can thank the presence of all the other planets in the solar system for the eventual harmony that was reached. It was a universal agreement in our solar system that all the planets would end up settling into a final orbit that wasn't quite circular. And that's okay. That's okay. And the Goblin's with us. How you doing, man? Did you use those binoculars yet? Goblin was one of our winners for telescope equipment. Yeah. Okay, so let's see. 18 shots so far. Now, the reason I show you an object like this right here is because this object is what would be called a reflection nebula, right? It's slightly blue, and it's actually composed of lots and lots of little bits of dust. And let me go back to our planetarium shot here first, just to show you. This planetarium is connected to our telescope, right? And this helps drive our telescope. Let's zoom out a little bit. So if we come down here, this is Rigel. Rigel is responsible for causing this object to glow and actually be seen. And the reason is because there's lots of dust particles in here. It's dark dust. But the dust is actually reflecting the starlight from Rigel. In fact, it's actually taking the blue light from Rigel, and in particular, it's scattering it back to our eyes. So by scattering that blue light, it means that we're going to see just the blue light. And so this dust is made visible by the effect of such scattering that goes on. And so we'll notice that dark dust that is out there in the universe, and there's plenty of it, okay, is actually very much so responsible for the blue nebulae that we often see All right, it's scattering the starlight, but it's only scattering the blue light in the spectrum. Remember, we have red, orange, yellow, green, blue, indigo, and violet light in the spectrum. And the red light, orange, yellow, green, that's fine. But the blue light is a shorter wavelength. And the blue, the indigo, and the violet side, shroom, that actually gets scattered because those little tiny dust particles are very good at redirecting the high frequency light, the blue light. And so that's what we see. And so that light goes in all directions, and some of it's coming toward us, and we see it. Hello, Izabela. Isabella's here. Yeah, and she's talking about Ronald having won the binoculars tonight on our radio show. Yeah, he does deserve it, because he's been a supporter of SkyTour Livestream as long as all the others that were here, but he's been a particularly staunch supporter for us. So, pretty cool. And Ray, I'm seeing all your messages. I just haven't. I've got 23 done here, 5 rejections. Let's go look at our track record here. In our full width half maximum filter, if a star image gets bloated higher than a certain amount, I reject it. And right now, I allow it to go up to as high as 8.2, and I'll reject it. And we've had an 8.01, so not bad. And as you can see, with this particular width allowance, we actually have stars that are actually round. So this isn't bad. We got a little bit of elongation, just a little, because we are, as soon as the sun sets in the desert, we get a lot of desert winds that kick up, and that goes away after a while. But by setting this number as high as I did, I leave the way open for there to be some elongation. Many times I'll have that number at 6.4. The Goblin says, I was going to use my binoculars to watch the space station fly over last week, but I didn't get home till almost an hour after it went over. Next time. Yeah, that's very cool. Just so you know, when you look at it with your binoculars, you're still only going to see a yellowish dot moving through the sky. But that yellow, it's the reason it's yellow, you may know this actually, Goblin, is because the massive solar panel rays on the space station are an orangey color. And so from a distance, that'll look like an orangey yellow to you. So the space station looks orangey yellow, and you're seeing the direct reflection from the solar panels. All right, let's go into our histogram here. And let's take the dark level and move it more up the peak here. This white curve is the average data curve. This yellow curve is how much we're intersecting. As you can see, there's a whole lot left out. And if I was to bring this rest of these up and bring this yellow bar up, you'll see that it gets really, really bright really, really fast. So that's too much data. So we have to bring it back down to something reasonable, like there. And this here is our dark level. If I bring it to the left, we climb down that curve, and more extraneous data comes in. And in fact, we can wash this right out. All right. But if I do it like this, that's too much. And if I pull it back like this, that's just about right. And again, this core of reddish color here is from the remaining sunset light that our very, very sensitive camera can see. All right, this will be the last exposure here. Okay, and it looks like that one was rejected. Yep. Oh, that was a bad one. So look at that. Wow. Yeah, that was a bad one. Talk about a big number. Look at that. That's a telescope total error. Wow, that's pretty cool. So the wind must have been particularly bad for a moment. If you think about it, we're pretty lucky to get as good a system as we can get out here. All right. we had a second failure. I'll write in what it is while we're waiting. This is the Witch's Head Nebula. Okay. There's our 30. So we're going to save. Even though it's got a little bit of the red, we can remove that later. Okay. And save exactly as seen. You'll see these green lines. This now shows that it's being saved out to our database and to our file structure. And if you want to get to it, you just have to go up here to skytourlive.org. And at skytourlive.org, you can scroll down and say, take me to cool photographs, to cool pictures. And it'll take you right to our server. You can look at all the pictures that we've taken for well over a year and a half right now up there. So that's pretty cool. And that's a free service. All these images are free for you. Oh, look, satellite. Zipping through. And it took 25 seconds for it to go that length of distance. So that's kind of interesting. So what we're going to do is go back to a 1 second time frame so we see what we're doing right away. And then what we'll do is then maximize and increase our vision here. All right, and we'll go back to our planetarium. And I figure while we're here, I am going to go into my data and grab that Sharpless catalog and Lund's Bright Nebula, Lund's Dark Nebula, and even the Caldwells, okay? And we're going to check that out. All right, so now we want Sharpless 2 from Ray, Sharpless 2-261. I believe we can find that. It sounds familiar, like we've done this before. We're going to find out. SH 2-261, Ray. Okay, there it is. Lowers Nebula. And that's going to be right there. Yeah, and we've done this one before. And if you look where it is, there's Betelgeuse right there. Okay. Here's the belt of 3 stars, Alnatak, Alnalaman, Mintaka. And so we're going to come up to Lowers Nebula. This is a request for Cosmic Ray. So here we go. Up to Lowers. You watch the telescope move up. Okay. There it goes. See it moving up? Kind of funky that, I'm giving something commands over 2,500 miles away. Okay. And now let's see here. I will refocus. I think the nebula's right here. But I'm going to... maybe not. Let me just do a quick 12-second exposure and see where it is. And I'll go into the live stack to show it because it'll be persistent. It won't go away. All right. Again, I'll have to refocus because we have a phenomenon called mirror flop, which occurs when you move the telescope up. There it is. Oh, it's to the right. Okay, cool. Right. Mirror flop is an interesting phenomenon, and it's the microscopic movement of the mirror when you move the telescope. It has mass, and so if you move the configuration, if you move it slightly to one side, it changes its position. And so that results in a wildly out of focus image. So what we're going to do is come back over here a little bit. Oh, I'm in 12 seconds. Duh. Let's go back to 1 second. There we go. And let's do that. So we're here. That's what we want, is right here. So we're going to move over now. Ray, you weren't with us when we did this last time? It's pretty. Okay. There we are. So now it's right there. And next thing I'm going to do is refocus, if you don't mind. So we're going to do that now. And for those that haven't seen our auto-focusing system, you're about to. Okay. So we've moved the focus in the positive direction out of focus. You know, it's equivalent of going, and then bringing it back slowly until it's perfectly focused. So we're now going to do that now, but we're going to let the system do it. Okay. So what's happening now over here, you'll see that we're starting to build a curve, a focus curve. And, you know, you're going to see these triangles make a curve that looks like this. And at the lowest part of that curve, that's where the star images are the smallest. Now, we also have the wind to contend with, and the wind is causing us to, you know, have to fight, you know, with the focuser. So that's a little bit of an issue as well. I'm going to try something here. Okay. So that said, we're waiting for the focus to happen. With some wind, you might not get a right focus right away. But we're going to watch and see what happens here. Each of these squares represents a sample that's been taken. I'm going to say the average is going to be right in here. So this is kind of like the average, and this is an outlier. They might get thrown away. So this looks like the average, and we're going to have the line's probably going to go right there. Yeah, there it is. Okay, so it ignored the bad point that the wind generated. So that's cool. All right, so let's now do a best focus on that. All right, so then it goes back and does this and back again. Effectively, that's what we're talking about. All right, and now we are focused, and now we just wait for the wind to stop. But the nice thing is, because we're using this, full width half maximum filter, what that means is, you know, if you look at the width of the star image, effectively, the width of that star image has to be small. And if it gets any bigger, it means that something is causing it to blow. Wind, like you see here, or something else out of focus. So until it's as small as I specify, it won't allow the picture to come through and be stacked. So it rejects it. And that's really cool. Cosmic Ray says, what hardware is the focuser? Well, it's actually what's called a stepper motor, Ray. You know what those are. It's a stepper motor on the focus arm. And it's a micro touch stepper motor. I modified it to fit on the Mead, and it was just very nice. It was a very nice setup. Okay, we're going to do a 30. No, I'll do 25 seconds here. Okay. And even if this goes wonky and we lose the image, it doesn't matter. It's not going to get recorded unless it's a perfect image. So that was that guy, and we're going to clear that. We're clear. 25 seconds. And we're in the full width half maximum filter. Red means it's rejected. Green will mean it was accepted. So 1 second from now, we'll find out. And the answer is... Okay, the first one was skipped altogether. Don't know why, but it was. All right, let's see what this one is. Okay. Okay, so these first two were rejected. They're way outside the 8.2. So the wind is pretty intense out there. But what we do is we wait it out. This is astronomy. Yeah, okay, so Ray, we may have to wait for the wind to calm down before doing this nebula, because that telescope is like a giant sail being blown around by the wind. Yeah, look how bad it is. The wind is really getting high out there. It's off our scale. Check it out. I've actually never seen wind that high. 12.66. Holy cow, that's a lot. 10.98, 10.43. This is going to be 10.82. But once the wind stops, it'll start pulling in. See, it's coming down now. 11.1. Ray, that question was asked of Calabos because he works for SpaceX. Okay, 7.3. So now that we know we have that capability, I'm going to lower this down a little bit more, and we'll make it just below 8, 7.55. Yes, we don't have the spider web indicator. Okay, I'll just raise it up a little bit. That's Lower's Nebula, by the way, guys. That's Cosmic Rays Requested Object. And I'll name it here. Okay. Hey, MPG, how you doing, man? Good to see you. Okay, we are in the process of trying to capture Lower's Nebula. And we're going to pull this in. Not too far. We don't want too much bad data. Ride that up near the top there to get a little more detail out of it. You call this the Elmo Nebula? Is that what you said? Izabela? The Elmo Nebula? Well, with the winds out there, with the post-sunset winds, we may end up having to wait a while. Yeah, it's pretty bad. Right now, the winds are pretty high. Excellent. Very nice. Yes, I know. The last 5 have not been stacked because the full width half maximum is too high. They were rejected. That's correct. We've only got 1 frame out of it so far. So, rather than wait, I think we're going to end up having to move to another object and then come back to it, Ray. I'd love to show you Lower's Nebula, but as you can see, the wind isn't cooperating. Okay, maybe we can come back, but I can tell you right now that no one wants to sit and wait. Ooh, Starlink. All right, let's do this. All right, let's go back here. And let's go down. Let's go see. I would actually like to do a shot of just the Flame Nebula. So let's try that. Telescope's gonna aim down a little bit, and we should have no problem picking it off. It'll be right there in the middle of our view. There it is, right there. And this is Alnatok right here, leftmost star in the Big Dipper's belt, perfectly placed. Okay, so we may have moved down just enough to stay out of the limelight of the winds. So we'll do a 25-second shot here. And come back in to our stack. And we'll have to get rid of the last one. Okay. And let's see what we got. It says it's still searching. So it might have had some wind while it was looking for a star. Yeah. But now it's interesting. It keeps saying searching up there, which means it's not finding a star to guide on easily. Not sure why. Try again. Wait the obligatory 11 seconds to get a guide star here. Hey Donald Kunzer, how are you? Okay, now we're guiding. So this next image, if the guiding is intact, I see it's going way up though. See these numbers, okay, you know, the numbers on, you see the right ascension on the left, declination on the right, that's the east-west correction and north-south correction. If the numbers start off in like 1, 2, or 0.3, 0.5, that's fine, but if they rapidly climb up to 6, 7, 8, it means that there's wind. And I can see that we are suffering from the wind. Here's what I'm going to do. I'm going to turn off this filter so it doesn't matter. And we'll see what we get. So this next image is guaranteed to come in. And we'll see how bad it looks. Yeah, see that? That's wind, man. That's a lot of wind. Jeez. You can see the telescopes from going this way and then a little bit left to right. That's crazy. I'm going to clear this and try again. Let's see what we get. Yeah, it's still searching. That means that, yeah, it looks like, I don't know, maybe tonight's going to be a bust because of the wind. Whenever there's a lot of wind, we don't want to, like, take too many shots. Here's what I'll do. I'm going to move our full width half maximum up to 8.45, 8.5, and So now if it's below that, it'll come in. This would have been like 8.6 or 8.7. Okay, so that one worked. So we are getting something out of this. This is a very interesting nebula for a lot of reasons, okay? Alnatok is helping to power this nebula, but there's some stars hidden behind this black dust that are also powering this nebula. This blue thing right here, that's a reflection artifact in the camera from very, very bright Alnatok. Oh, I don't know, Izabela says, so it's not worth going to Hubble's Variable Nebula. I'm not sure about that, because Hubble's Variable Nebula doesn't need very long times, you know. Mike Townsend says, dang, I was going to put in for a special request for the black hole in Taurus. Actually, there is, you can see the star that's associated with this black hole. And that's pretty interesting. But it's just a star. It'll look like a star. You won't see any kind of black hole stuff. DPFX 9999. How you doing, man? Okay. The wind is up, and that would have ruined this exposure, as you can see. But with the filter in place, it rejects these because they're too, they moved around too much. Mr. Django, how are things in Belgium? Thank you for dropping by. And DP, I just gotta say thank you for the kind words about these stunning images. Very happy to provide them. Very excited to do so. You know. Michael Hedrick says, how is it possible for some big stars to have such low density and still shine? Well, that's actually a very interesting question. Here's where that question originates, I imagine. If you look at a star like the sun, it has a certain density. But if our sun runs out of its hydrogen, then the core begins to contract. And when the core begins to contract, the radiative pressure outward increases and it bloats into this giant red giant star, and its density decreases. But the thing that's actually making the star shine is the very, very compact core that's still in the middle there. And in stars like that, where the red giant phase is reached, guess what? You might actually see a condition where you can see a bright, shiny core inside the star, and outside is not as bright. And so you can see right into the star and see the core in there shining, and the rest of the star is more tenuous and low density. So that's a very strong possibility. Mr. Django says everything fine, thanks. Just the weather is still cloudy. I don't like cloudy weather, man. I tell you that. Sorry you have to go through that. Michael Galea, hello, Mark. Thank you for your work, showing us the beautiful pictures. Oh man, of course. I mean, look at this. This is gorgeous. This beautiful nebula. We're gonna zoom in because we can now. We got enough data here to kind of zoom in. Look at all the detail in here. This is crazy beautiful. And up here you'll notice a subtle red. This is not the sunset light. This is actually an emission nebula here. And you can see this beautiful texture up here. This is going to come out. All right. The modeling you see, that's noise. This modeling you see is noise, and that's going to go away. All right. So let's bring out some more details, shall we? Let's color correct for one. All right, there we go. And let's ride up our black level to darken the background and call out the detail in the foreground. There we go. And now you can start to see the details here appearing. Now what's funny is I've been photographing the flame all my life, and until I started using this telescope, I never saw these two reflection nebulae, these nice blue reflection nebulae. Never saw them. Hey, John Bailey, how are you? John Bailey is in San Francisco, and he says, what are iron stars? All right, well, every massive star that's above 10 or 12 masses of our sun will actually form a core of iron. It'll be able to get to iron as it's doing hydrogen fusion to helium fusion, and then carbon, oxygen fusion, and eventually it gets to number 26 in the periodic table, and that's iron. And the iron can't be fused into anything more because the star can't put in enough energy in its ordinary processes to fuse iron into anything else. It takes more energy than the star has to actually fuse iron into anything else. So iron is the logical stopping point for the bigger stars. So these stars that have iron in their cores are usually, well, in fact, definitely destined for supernovae. They will eventually blow themselves to kingdom come when the time comes. And most likely they will only live a few million years if that's the case. And so that's one of the things that is the mystery of the universe, is how long these stars can live. We see and engage how stellar evolution progresses. And when I was getting my degree in astronomy, one of the things I had to do was actually build a star mathematically, from the core all the way out. And I got to tell you, it's no small feat. You have to pay attention to all kinds of things, collisions between protons in the outer part of the star. You need to care about that. What the protons do, how neutrinos that are produced in the solar fusion or the stellar fusion process, how the neutrinos affect the energy budget of the star as they are emanated from the star. You have to take into account how much mass in the star is lost every split second. Okay, because stars like this one here, this is Alnitak, all right, the leftmost star in the Orion's belt. Stars like this are losing tons of mass every second, and the biggest stars can lose whole solar masses in a short amount of time. So we're talking here about a moving target. We have to try and figure out just how much mass is being lost. We have to figure out how much the star is up against, what's going on in its processes, where it is in its life, so to speak, life cycle. So there's a lot to consider with a star, but the iron stars are going to be those that have iron in their cores. The sun does not have iron in its core. It will never have iron in its core. Only the really massive stars, many, many times the mass of our sun, will have the ability to fuse into iron from the previous elements in the periodic table. Okay. Let me know if that helps. If you need more understanding, I'll be happy to tell you. So if it does have iron in its core, it's going to be very destructive. At some point, DPFX, yes. At some point, an iron core, actually, I'll spell it out for you. Here's how it goes. Okay, let's suppose you have all these fusion paths in your star. The simplest one is hydrogen to helium, then helium to carbon, carbon into nitrogen and oxygen isotopes, and then it goes all the way down the periodic table now to iron, number 26. Now, let's suppose you're fusing material into iron. Okay, so now those previous atoms are fused into iron. The iron is now sitting in the core. Nothing else can happen. It's sort of like it's stuck in the throat of the star. And it's right in the very, very core. So you cannot get anything, more out of an iron core. So now around that iron core, other materials start to fuse. You'll get, you'll have shells. Outside you'll have a hydrogen shell still fusing what little hydrogen's left into helium. You'll have a helium into carbon, carbon into nitrogen and oxygen, and then you'll have other isotopes being made, and then you'll have iron being made, okay, and you'll also have nickel isotopes in there as well, right? And so, but the iron is the stopping point, and then eventually the star is going to go supernova when it runs out of all those other elements that are fusing in the shells around the star. It's like an onion skin. And when that all fails, okay, you'll know it if you could see into the star, you would know that you're on your very last day of existence as a star if you see silicon being fused. When silicon starts to appear, literally that process lasts for 1 day. And after that, the star explodes into a supernova. And if we're watching the heavens from here, how would we know there's a supernova coming? Actually, it's very clear, because we'll actually see long before the supernova even erupts out of the core, moves through the star, reaches the surface of the star, and explodes outward. The neutrinos that are produced, a burst of neutrinos, appear and are burst out of the star and make their way all across the universe. So if we detect a stream of neutrinos coming from Betelgeuse, for instance, which is right up above this up here, okay, then we would know that Betelgeuse is about to go supernova, because the neutrinos will get here first, okay? And then some hours later, we would see the light change. Maybe even a day later, we'd see the light change as Betelgeuse erupted into supernova. Why is that? That's because Betelgeuse is so big that if you put it where the sun is, it'd go out to the orbit of Jupiter. Okay, and it takes time, for light to get here from Jupiter, right? So that amount of time is not exactly how long it takes for the neutrinos to escape, moving at light speed, because the neutrinos are also colliding with other things inside the star, and only 1 in 1 billion neutrinos actually get out of the star. As such, we actually do have many neutrinos that reach us from stars like that. So the neutrino stream is the indicator of what's coming, and if we see a neutrino stream, turn that telescope toward the source band, because we have a supernova incoming. Cosmic ray, that blue splotch I mentioned earlier, that's actually a lens flare from Alnitak right here. Notice it's symmetric across the field here. John Bailey says, how long do these stars live? Well, stars like Alnitak are not long-lived, okay? The hottest, bluest stars there are the O-type stars. And O-type stars don't live a long time. They live a few million years, okay? As opposed to our sun, which will last 10 billion years, and we're about 5 billion years into that, okay? So these stars will last a few million years, and then they'll run out of their fusion products, because they burn through their fuel very, very quickly, and they start burning other things into later elements in the periodic table. It just keeps going. So in the end, it turns out that we will have a star like this, like Alnitak, that might last a few million years. In fact, I'll tell you a little thing here that's pretty cool. 4.2 million years ago, Lucy, Australopithecus afarensis, in Africa, walking around Old Divide Gorge, you could just imagine Lucy looking up and seeing the bright dots in the sky, and not capable of thinking what they are. But if Lucy looked at Orion, Lucy would have seen only 2 stars in the belt 4.2 million years ago. Because back then, Alnitak, right here, probably wasn't there. All right, this winked on sometime since that point, and it's only going to last a few more million years. and then it's going to go absolute supernova. Man, I would love to be. It's about 1,500 light years away. I'd love to see that. I'd like a front row seat to that. So Michael says, could Betelgeuse help us see the space in ways we never saw before by using its supernova light? That's interesting. Gravitational distortions. Betelgeuse is around 750 light years from us, so it's possible that Betelgeuse the data coming to us from Betelgeuse could be helpful to us. Now we're getting all this subtle detail here. Look at that. Okay. It's possible that it could help us see what's going on. We'll see light echoes maybe. That would be kind of cool. A light echo is a bright burst of energy that leaves an area, and it actually will basically illuminate the dust on its way out, the dusting and an ionized gas on its way out. So those are called light echoes. Cosmic Ray says Lucy would not have the International Astronomical Union to contact. That's correct. The IAU is the governing body for all things stellar. So if you discover a star, the IAU will decide whether you can name it for yourself. Most likely the answer is no. We got 17 exposures that are good and 21 that have been rejected. This would look like a real terrible image if we let these all come in. Yeah, light echoes, exactly, Michael Hedrick. Light echoes, we've seen them before. Supernova 1987A, we saw an expanding shell of light leaving the supernova into the adjoining nebula. So, because the universe is so big, and even though light's the fastest thing in the universe, it certainly doesn't appear to be moving fast when we look at it. If we looked at the light echo, it'll just look like it's sitting there. You know? Come back a week later and it might have moved a little bit because it's so far away that the light's taking time to move. You know, it's still moving 186,282 miles per second. That's 7.5 times around the Earth in a second. It's still moving that fast. But after you get a real long distance away, well, I'm sorry, but you're not going to see too much movement. All right. Cosmic Ray asked about a mass damper to counteract the wind push. Yeah, actually, that's called a massive instrument ray. Basically, if we made this thing out of titanium and lead, okay, then the wind would have very little opportunity to push it around, you know. But you're also going to get resonant frequencies, you know. Standing wave set up in the tube, as the wind goes over the end of the tube, you might get a buffer, like a inside the tube, and that momentary standing wave could vibrate something and cause the problem. It's so sensitive. Look at that. Look at the level of magnification here. Then again, look at how beautiful this is. Look at that. It looks like a piece of art, doesn't it? Looks like a piece of art. This is why I wanted to do this. Let's come back here. We're running out of good exposures right now. Okay, let's see here. Let's zoom out. There we go. I'm purposely above what is actually right about here, because what's here is the horse head, and I didn't want to take away from the beauty of this region. I wanted to capture this piece too. That's really pretty. 2 reflection nebulae, 2 reflection nebulae. Hey, that's pretty cool. Actually, it dampens it, Ray. It doesn't stop it. But you're right. I mean, they have those earthquake dampers, which counteract the vibrations. MPG says, Mark, what led you? I'm assuming you mean to the new camera model. What made you decide on that model? Oh, okay, excellent question. This camera delivers the best arc seconds per pixel rating of any camera. What's that mean? It means that when you take the micron size of the pixels, which is 2.4 in this camera, and you multiply it, times the focal length, right? You get a arc seconds per pixel rating. I'll have to get you the formula because I think I just said it wrong. But what happens is you end up getting a value, and our value for this camera is 0.98 arc seconds per pixel. Okay, so that means each pixel has just about 1 arc second per pixel. And for this telescope with this particular f2 configuration, very fast optical system, 503 millimeter focal length with our wide field system adapter on it called a Hyperstar. This telescope is optimally perfect with the 183 MC Pro camera. We had the 294 MC Pro and still have it, but it's not the optimum camera for this telescope. We were actually missing data from it. It wasn't as good for us. And so the 183 MC Pro, by far the best camera. The next telescope is going to have the 2600 Duo on it. And the 2600 Duo is going to be a camera that will guide the images for us as well as photograph the images for us all at the same time. And we've already got that budgeted for. And the new telescope is already budgeted for as well. Yeah. And with what's left over, we're going to try and get a solar telescope in order to do solar astronomy. And that we would do on the East Coast here. So that's the idea. Because why should I ever get any sleep? I shouldn't be able to sleep at all. Okay, we're not getting any more good shots out of this. That one was close. All right, so we'll just save it here because this is not. We're gonna be the flame region. There we go. Okay. Still, that's really pretty. That's going to produce a really pretty shot. All right, so we'll save it. Now, as we save this, within 30 seconds or so, it's going to end up on our server. So if you go up here, skytourlive.org, see right at the top there, skytourlive.org, and scroll down, the next box you reach is going to say, take me to the cool pictures. It's going to take you to where these are stored, and read the instructions for how to get at them there. Jessica S is with us. Hey, Jessica. You were here for a while. Sorry, I saw you, but I didn't get a chance to say hi. Very cool. All right. So there's the flame region. And just one more time, let's zoom in on that. Look at that. Look how subtle the detail in there. I'm going to show you something. Growing up, all I ever knew about the Flame Nebula was like this much of it. That's kind of what I remember seeing. Only that. Never, ever anything like this. Where you see these subtle clouds reaching out here like this. None of that. So this is so cool. I had so many actual firsts with this telescope. Firsts, you know, the first time I saw a supernova remnant was with this telescope. First time I saw the helix and saw the beautiful inner radial structures was with this telescope. So it's really amazing. You know, this is really just a beautiful instrument, and I'm glad I could share it with you guys. All right, so let's go back now here. Zoom me out, and let's see here. I guess we could actually go to Christmas tree cluster. Well, we're going to go to Hubble's Variable Nebula first. Let's make sure it's visible. The edge of the telescope building here could be blocking it. That's why I'm saying that, but I don't think it is. The Hubble's Variable Nebula is this tiny nebula, there it is, that changes brightness depending on a particular star that's inside a dark cloud that we cannot see. All right, there's all dark clouds here, dark clouds of dust, and there's one particular star inside that dark cloud that has other dark clouds of dust orbiting it, and as those dark clouds of dust get in the way of the starlight, the starlight falling on this other dust cloud out here changes in brightness. And you might say, well, how in the world can you do that? How do you know that? We know that because of spectral analysis of the cloud. That helps us figure this stuff out. Okay, Donald Kunzer says, will you do a mosaic of the Orion area with this scope? As a matter of fact, Donald, I've been trying to get to that because I do want to do a mosaic. Oh, look at us. Look at that wind. Man. Yeah, I'm trying to do that. Daisy and Zoe. Love the Flame Nebula. Oh, yeah, it's pretty cool, isn't it? Hello, PG. That's Petita. I know Petita. Petita in Pennsylvania. Oh, Donald Kunzer, yeah, I can't do this mosaic tonight, unfortunately, because just look at the screen. You can see the stars getting pushed around. So it's unfortunately impossible right now. Yeah. All right, but what I'll do is let's see if we can get a couple shots of the Hubble's Variable Nebula here. Zoom in a little bit. Oh yeah, it's hard with the wind. I'm trying to outlast the wind, but I don't know. Well, let's try a 20-second shot. That's all you need for Hubble's Variable Nebula. I can tell you the first one's not going to work. Alright, we'll come out of here and go into our live stack. And then we will delete this, but it's not gone. It's up on our server. Izabela put the address for you all up there. Oh, look at that. It came out. Good. Let's move this. So there's Hubble's Variable Nebula. Beautiful little nebula. Alright, it's a beautiful nebula. Okay, and as we pull this over, darken up the background, you can see this wispy structure now. This is a dark knot of dust in here, and it's inside this dark cloud that the star that's got its light escaping to illuminate this cloud is hiding in. Hey Fantasy X, what's up? was just reading chat. I probably should have. Yeah, see how the wind did that number on us? Well, I always keep the Hubble's variable nebula because we compare them to others. And we've actually seen the change in brightness, which is pretty cool. There we are. Oh, Michael Hedrick had a question above. Where is Michael Hedrick's question? The first data released to the public from the Rosetta Sky Survey comprises an X-ray view of the sky over Earth, encompassing almost 1 million high-energy cosmic sources, including over 700,000 supermassive black holes. Is that the question, Mike? That was a statement, I thought. Calabos. Thanks, man. I'll be seeing Calabos out in Palm Springs at the Contact in the Desert, where we will be giving away telescopes as well. That should be fun. Yeah, that's an interesting survey. Oh, and you said, Mark, what? And I don't know what that was in response to, so I'm sorry. Yeah, I thought Calabos was leaving too. I think he is. No, Calabos is great. Did a radio show before this. Did this now. And okay, there we got another one. Yeah, Ray says Arizona site needs a weather station. Yes, it does, and we're actually actively looking for one. Yep. I do not know more about that survey. Oh, good. We got 3 more shots here, so we're up to 7 good shots. Now you can start to see some of the intricacy here taking place. Let's see if we can enhance this a little bit. Let's add a little sharpening. Okay. Let's reduce color noise. There we go. See? We can pull out some good detail. No, Ray says, what type of weather interface? Wireless? No. I actually want all cabled. Everything has to be connected with wires. And the reason is because Wi-Fi goes out, Bluetooth is lost, and usually you have to be there to fix it. With cables, no problem. In fact, our all-sky camera that we're putting in is much easier to do as a Wi-Fi installation. But I chose a wired installation, and our Wi-Fi camera now really looks very, very nice. And I will actually show you that. I want to show you what we got right now, what we can do. Okay, so let's see if I can do this here. That ain't it. Okay. Let's see about this. Okay, here we go. Alright, so if you look at this image right now, this is the Wi-Fi camera. I'm sorry, not the Wi-Fi camera. This is our new night vision camera. I built the housing, I built the camera, not the camera, but I built the entire concept up from an existing template. If you notice, we can zoom in quite a lot, and we actually have an unbelievable view. Like we're in, here is Aldebaran in the Hyades. There's the Pleiades, very, very clear, right? Down here, here's Orion right here, the Orion Nebula. You can see that beautiful pink color, the Orion Nebula, the red of Betelgeuse. And then here is Gemini twins, Castor and Pollux, and you'll see this little fuzzy thing right there. That's Messier 35, a cluster up in Gemini. And this is not out in Arizona. This is right outside. It's literally 25 feet from me. This is our view here. Okay. So this is our new camera. And one of the nice features of this new camera, which I'm going to show you right now, is what this can do. Let me go here. Let's go back to our website here. This is our site. Check this out. I know it's a little bit small, but I wonder if I can enlarge that for you guys. Maybe I can. No, okay. Here, watch this. So here, this is what's going to be on the website. When you do this, you click this. Now you get an overlay of the constellations, right? And the locations of things. So you can actually see, where Castor and Pollux are and where Messier 35 is. Now check it out. Messier 35, watch this. You hover over it, and you click on it, and now go see Messier 35. Using the WikiSky application is tied into this. So this is really pretty. Here's the Pleiades, Messier 45, right? And let's see if I can, is it here? Yep. So there's the Pleiades as seen here, right? And of course, it's just a beautiful